All right, so let's continue our discussion on Fourier analysis on finite abelian groups. So in the last video, we have defined the Fourier transform of a function, the Fourier transformation of a function, which is defined like this. And then we have seen the Fourier inversion theorem that says how to get f back from its Fourier transform. Now we will come to the main theorem of of the study of Fourier analysis on finite groups. In fact, Fourier transform is the main instrument to study the group algebra LG. Okay, so this is the main theorem that we are going to prove, that F maps to its Fourier transform. It's an isomorphism between the algebras, and these are algebras over C. So the isomorphism of the algebras LG with pointers addition convolution, and then LG hat with pointers addition and pointers multiplication. Okay. So as I said that in the theory of Fourier analysis, the Fourier transform is the main instrument to study the group algebra of a group. Okay. So yeah, so in view of this theorem, I think what I just said, that this Fourier transform is the main instrument, I think you should be able to have some feeling for that. Okay, so let's prove it. So first of all, these are vector spaces over LG. So an isomorphism between algebras to algebras means, in one hand, it's isomorphism between vector spaces, that's a linear isomorphism. On the other hand, it is also an isomorphism of rings. Okay. Now let's see. The proof of this is actually not quite easy. In fact, most part of the proof is in fact trivial. So if you recall the definition of this f to f hat of f hat, that is some scalar times some scalar that is order of g times the inner product of f and chi. So from the bilinearity, or more technically, the linearity in the first variable of the inner product. So from the linearity, it is clear that from the linearity of the inner product, it is clear that this assignment is linear. Now, so linear part is gone. We want to show it is injective. The injectivity is obvious from the Fourier transform, because if f hat is 0, then the Fourier inversion theorem shows f itself is 0. So injective, so linear, injective, both are done. The surjectivity is also obvious, because because g hat has exactly order of g number of elements. So the order of g hat and order of g are same. So this has the dimension order of g, this is the dimension order of g hat. So therefore, these vector spaces are of same dimension. So a linear map, injective linear map between the two finite dimensional vector spaces of same dimension must be surjective. So from that, the surjectivity is also obvious. So the linear isomorphism part is over. We now have to show it is ring isomorphism. In order to show the ring isomorphism, what we are just left is, we have to show that the product is being preserved, because the addition because the addition preserving nature has been already taken care of when we considered the linear isomorphism, when we just proved it a linear isomorphism. So now we are just left with the product. So what we are going to prove is the Fourier transform of the convolution is same as the actual pointers product of the Fourier transforms. So this is again exactly similar to the scenario of classical Fourier analysis over real line. So there also we there also we had this, that when you take the Fourier transform, when you take the you first take the convolution product and then you take the Fourier transform. That is same as first you take the Fourier transform and then take the pointwise product. That one, the importance of this formula was the following, that the way this convolution is defined is actually very complicated, so that sometimes it becomes practically impossible or very hard to compute the convolution of two functions. So in that case, what one should do is, in view of these, that we should take the Fourier transform. There we take the pointwise product, uh, because pointwise product is relatively easier. Then one uses the Fourier transform, Fourier inversion to get back to the this the convolution product. So I mean, once we, so again let me repeat. So direct computation of the convolution product becomes almost I mean, the direct computation of the convolution product uh, uh, becomes quite difficult. So what we do is we just take the Fourier, then take the Fourier transform, then the pointwise product, then using Fourier transform, we then come back to the convolution product indeed. And this happens to be, and for most of the practical purposes, this happens to be rather easier compared to computing the convolution product directly. Okay, so let's try to establish this formula, which shows the map is a ring homomorphism. So let chi be any character. So the value of the Fourier transform of the convolution at the point chi is this from the definition. Now you just open it up using the definition. And once you open it up, now you also open this up. That is precisely this. Now what we did do is, since we are working with finite thing, finitely many summands, so we can interchange the order of the summation. So the interchanging the order of the summation, this is what we get. Now we will make a substitution of changing variables here. So we'll make the following change: z equal to xy inverse. So as earlier, x runs over all element in G. So xy inverse for a fixed y, that also runs over all elements in G. So therefore this is that. Now we recall that for an abelian group, a character is same as a homomorphism from the group to S1. So this is chi. So this is chi z times chi y, and then chi y you can to pull it outside. So this is what it is, and this is according to the definition. This is chi hat. This is phi hat of chi. So for each y, you have this term phi hat of chi. So you can take it out, and then using distributivity, and whatever is left out is just according to the definition psi hat of chi. So that shows that the Fourier transform of the convolution is product of the Fourier pointwise product of the Fourier transforms. So in view of this and the earlier part where we have established is a Fourier transform establishes a linear isomorphism. So putting this together, our theorem is complete. And let me again recall what the theorem says. The theorem says that Fourier transform, what we have defined in the last lecture, can be realized as an isomorphism from LG to LG hat. And on the left, on LG has convolution, whereas the LG hat is equipped with the pointwise product, pointwise multiplication. Okay. So once this isomorphism theorem is there, now we will look for a few applications of Fourier, a few applications of what we have done so far. In fact, we will prove the two things which are very well known and important in the classical abelian harmonic analysis. So the first thing that we're going to see is the Heisenberg uncertainty principle. So the proof of which is actually indeed quite easy. So what the principle says that suppose so it's a finite proof version of the classical Heisenberg uncertainty principle. So it says that suppose you have a function and for a function, let's define its support as the set of points where it is non-zero. So the principle says suppose you have a function, then the product of the number of elements of the support of f and support of f hat should be at least order of g. And regarding support of f hat, you should also the support of f hat that is defined as analogously as support of f, because f hat belongs to LG hat. F hat is a function from g hat to c. So it's defined in the similar way with that of the support of f. And this is the statement of the Heisenberg uncertainty principle. Okay, so once that is there, the proof of this principle is very easy. First of all, we use Fourier inversion theorem. As I said that the Fourier inversion theorem is one of the most fundamental tools. When we proved that the Fourier transform establishes an isomorphism between LG and LG hat, there we indeed took the help of Fourier inversion. So now we will also look for here also we will apply the Fourier inversion. So f of x is this according to the Fourier inversion. Now you just apply triangle inequality. So you have this sum. So sum of these summands might be 0. So thus, if you just disregard the 0 summands, so then you have been bound that so all the non-zero summands you can bound it from above by their maximum. And once you do that, then this is equals to the number of non-zero summands times the supremum. So the number of non-zero summands is defined as the support of f prime. So for every x we have this. So since yeah, on the other hand, from the definition of f hat chi, so the definition of summation fg chi prime g, so using triangle inequality, we have this. So again, as earlier, if we disregard the zero summand, zero terms, so whatever is left that can be bound, that will be less or equal to the supremum of less or equal to the supremum times the non-zero terms. And the non-zero terms is by definition support the cardinality of the support of f. So therefore what we get is so this holds for every chi. So what we get is the supremum. So the supremum over since this holds for every chi, the supremum is less or equals to this times this. Now we feed this inequality in the above inequality to get that for every x. So once we replace this, once we use this is less or equals to that, so then we get mod of f of x is less or equal to the coordinate of support of f hat times support of f divided by order of g, and then this fellow, right? So this is what we get for every x. So hence the supremum is less or equals to that. Now we use the fact that the function that we have considered in the statement of this principle, so we took the function to be identically not identically 0, so therefore its supremum is a non-zero, in fact a positive number. So now when we divide the inequality, both sides of the inequality by this positive number, we get the desired conclusion of the Heisenberg's uncertainty principle. We get the desired conclusion. Okay, so this is one application of Fourier inversion theorem. Now I will finish the Fourier analysis on finite abelian groups with another very important result, another very important concept or tool, which is called the Poisson summation formula. So to state the formula, we need to define something. So let's first do that for any finite abelian group G and a subgroup H prime. So we H parp is the set of all characters of the set of all characters. Sorry, I think here is a slight mistake in the notation. So G parp will be actually replaced by G hat. So okay, so keeping that in mind, let's again say what this collection is. This is the collection of all characters which are identically trivial on H. The character, all the set of collection of all characters of G which are identically trivial on H. It is easy to see that this collection is a subgroup of G hat, and in fact we will now establish a nice isomorphism. For that, let's observe that for any such character which is trivial identically on H, if we define another character chi, if we define the following chi prime from G mod H to C as chi prime of GH equal to chi G, so for any chi, we define chi prime like this. The well-definedness of this chi prime is easy to see in view of the fact that chi is identically 1 on H. So this chi prime, so given chi prime is a map from G mod H to C, and again from the definition, since chi is a homomorphism, so it is clear that chi prime is also a homomorphism from G mod H to C. And furthermore, one has the following diagram that chi prime and chi are connected, chi prime and chi and this projection map, all these three maps make this diagram commutative. Okay, so now this assignment that chi maps to chi prime is it is easy to see that it's actually an isomorphism from H parp to the dual group of G modulo H. Again, let me just explain. So given any chi, the chi prime is a homomorphism from G modulo H. So therefore chi prime lies here. The chi prime is a homomorphism, and chi prime is a homomorphism, and this assignment chi maps to chi prime is indeed is an isomorphism. For example, if you want to see the subjectivity is very clear. Suppose you take some chi prime here, then the pre-image chi would be just the composition of chi prime with the projection map. So basically everything follows if you keep this commutative diagram in your mind. So thus these two groups are isomorphic. So in view of this isomorphism, we have the following, we observe the following, that suppose you fix y in G, then summation chi y, where chi belongs to H parp. Now we will shift to chi prime, and the way chi and chi prime are connected. So chi y is precisely chi prime yh. So here taking summation over all chi in H parp is saying as taking summation over all chi prime in the dual group of G modulo H. And for that we know for this we proved well, this is equals to this, and this is what and we know what it is from when we studied the characters of regular representations. This is equals to the order of the group when y is in, so when yh is the identity element of G module H, that is when y is in H and 0 elsewhere. Okay. Now we are almost towards the end, so we will now state the Poisson summation formula. What it says that for any function defined over G, so this is these two things are equal for any G in G, and in particular if you take G equal to identity, this then you get this, which is the form of the well-known Poisson summation formula of classical Fourier analysis. So we will prove this. The proof of this is again we make a reduction since so if you look at the both sides that you are supposed to show equal. If you look at both the sides, then you see both the sides are actually linear, because f hat is, or f goes to f hat is also a linear, it's also a linear map. Okay, so since we have observed linearity on both the sides, so in view of that, it is now enough to show this formula when f is a function of this type, that is ex. So where ex in x belongs to G, because this is actually a basis of LG. So once we can show both sides for basis elements, then using linearity with it immediately extends to any function in LG. So henceforth, we will be proving this formula for f equal to Ex. So when f equal to Ex, we will first see what happens to the left hand side. So then this is the left hand side, and it is since Ex takes value 1 at the point x and 0 elsewhere. So this is exactly, so only one term will survive. So when GH, I mean, what I mean is the H for which GH is X, only the summand corresponding to that H will survive, rest of them will go. And I mean, if provided G for some H, GH is X, that is X belongs to GH. So in that case, we will get 1 by order of H. And if X doesn't belongs to GH, then evidently this is 0. So the left hand side is basically 1 by order of H, or 0. Accordingly, X belongs to the coset of belongs to the coset GH or not. Now we will see the same holds for the right hand side as well. So in the right hand side, we have in right hand side, this is what is appearing. So for that, let's compute what it is. So from the definition, it is easy to see that this is just conjugate of chi x. So now in view of that, we get this equals to that. Okay. So remember that chi is a homomorphism, so you can write x as G into G inverse x. So therefore chi x is the product of chi G times chi G inverse x, and since a conjugation is there, so the chi G bar times chi G will be mod chi G square, which of course has to be 1, because chi takes the value in S1. So therefore this sum is this. Now we use the observation that we have made here, that once when we are supposed to compute a sum like this, then we can convert it to a sum like this in the dual group of G modulo H, and here we know what it is. This is this or that. So now we will simply use that. When we will use that, we get, so this is exact. So we take the conjugation over everything. So then what comes under the so once we take the conjugation out, so what comes is just sum of the uh, sum of chi of G inverse X when chi runs over all elements in H bar, which in view of the previous observation is precisely this. And now we know what it is. If this is H, so G inverse XH is H, is same as saying X belongs to GH. So this is therefore this sum is the order of this group if X belongs to GH or zero otherwise. So since here we have all this factor on the right hand side, so when we multiply when we multiply this by the order of 1 by order of G, then this here from here the order of G term will cancel, so we'll get 1 by order of H if X belongs to GH and G0 and 0 otherwise. So that proves the Poisson summation formula. So let me just quickly recall. So in this video, we talked about we first proved the most fundamental theorem of Fourier analysis of fundamental theorem of Fourier analysis on finite abelian groups, namely the Fourier transform can be realized as an isomorphism from LG to LG hat. Then as an application of the Fourier inversion formula, we established the Heisenberg uncertainty principle, and then finally we proved the Poisson summation formula for finite abelian groups. Okay, so this is what we have done in view of the linearity of both sides. We just in view of the linearity of both sides, it was enough if we show both sides are equal when f is a basis function, namely some ex, and the left hand side is can be easily seen to be this. For the right hand side, we have to do something. So we get a sum over all over all characters in H bar, and then we convert it using the isomorphism from H bar to the dual group of G modulo H. Then we convert the sum to a sum of characters on G module on the dual group G modulo H, dual group of G modulo H. Then we just use what and then because we convert it, and the reason for conversion is because we know what it is now, then we just apply, and then from that the formula is put. Okay, so I will stop here.